This is an introduction to the internal drive system for a omnidirectional drive BattleBot. The system I designed is based really off of two parts. The first is this 6384 motor. I have a number of these sitting around, and the second is this, which is the internal piece of a clutch system I had for a much larger robot. It was actually around 4,000 pounds. Now this started out at 8 pounds, and I put it on the lathe and I turned it down to see just how light I could make it, to see whether it might be viable. And I really did remove a ton of weight. So I'm going to try, based on this clutch system, to fit the design around it. All right, let's get into CAD. This is SolidWorks, obviously. There's the two motors, twin motor design. They say they're 4,000 watt, but it's Chinese 4,000 watt, and if you know what that means, you'll be lucky to get a momentary peak of 3 kilowatts out of them. But that's plenty. Two 15-tooth 1.5 module gears at the front. And these are outrunners, so the first thing I have to do is add a support bearing in the back. Now that doesn't fix everything. The magnets are still cantilevered, and under high G loading they could impact the stator. There's not a whole lot I can do about that. There are motor designs that have bearings front and back. I'm just going with what I have. I had this idea a number of years ago to turn a aluminum tube and make a aluminum heat spreader fins for motors for outrunners with them. This is really, if you think about it, it's just a multi-start thread, and I can do it on my CNC lathe, but it would take time and effort. And right now it's an idea. I don't know if I'm going to have time to complete it. The next part is the internal axle. This is made of 4130 DOM tubing, and I have a bunch of this laying around. That's the reason it's picked. 1.25 inches in diameter nominal. The front and back pieces are really registration pieces for the front and back structure. I have two types of this, and there's a thicker and thinner. This is the thicker. I don't know that I'm going to need that much strength. Basically, this needs to be light enough that I can afford heavy armor on the outside. And putting extra mass inside here means I'm going to lose protection on the outside. That's the trade everybody makes. This is the structure that holds the two motors on the front. As you can see, there's a machined out section to allow the wires to escape. This is made out of the 0.89 inch aluminum 6061 plates that I have. There's standoffs here for the gearing. Next, the back. This is really a minimum structure. There's very little here. The idea is this load in the back is not very extensive. If you need maybe to be able to support 200 or 300 pounds of load at the back, and this by structural analysis this will do it. This also supports up top here the mounts for the speed controllers, one for each motor. Speaking of which, there are speed controller mounts mounted two different ways. For the design, I started looking at things. I don't know until I start futzing with it whether the wiring is going to work or not. In this case, the speed controller is mounted facing out, which puts it farther away from the center. In the other case, the speed controller is mounted in, and that puts it closer to the center, but there may be clearance issues. You look at a VESC, this is just a brick to represent the VESC. When you look at them, the distance between, the clearance distance between the motor and the edge of the VESC, remember there's wires that come out the side of the VESC and they have to turn around and get out the center axle. So obviously with an outrunner, if it's spinning and it touches wire, it's really, you're gonna have a really bad day very quickly. So we'll find out whether I can get the wires to go or not, and if we can't, then I'll have to go with this larger design here. This is the first stage of the gearing system. This is a combination of gears that transmit torque to this center gear and then through a friction clutch transmits it to the sun of a chain planetary. Now I'm going to switch here real quick. You might recognize this. This is the center of that clutch device that I showed. And so this is the build up of the first gearing assembly. Now these bars are 3/8 apart, 375, and that's a number 35 chain. So this piece is effectively a chain that's held in an exact circle. That's the center, that's the planet, the sun of a chain planetary. I've always wanted to make a chain planetary, so this is my excuse to do it. This is connected through a friction disc. This actually, I have these from the original clutch design to a gear, the center gear. Now note that the center gear is hollowed out. This represents the edge of structural analysis for this piece. This is how thin you can make it to match the amount of material left in the gear with the strength of a tooth. There's no use having an excess amount of material in the center of the gear if your tooth is going to fail before the gear fails. So I did a lot of iterations of structural analysis to show that this is sufficient. There is a spacer made of Delrin in here that just keeps everything centered. Shown here, there's a wave, what's called a wave disc spring, right? And these are basically linear springs that put pressure on between two flat plates. In this case, you can stack these springs 1, 2, 3, 4 thick to get the level of load that you need. This is the nut from the clutch assembly that I had. I had to spin this down a lot, but it will load those wave springs into this friction disc, and it keeps the transmission of torque between the gear and the sun of the chain planetary. All of this spins on a iron copper bushing, and there is a thrust bushing at the back to keep it from impacting the other structure. All right, so we've gotten the torque from the 15 tooth to the center gear, from the center gear transmitted through this clutch to the sun of the chain planetary. Now let's look at the planets. This is where I ran into a compromise on how much gain or gear ratio I could get out of the chain planetary. I wanted to get a bit more. The problem is that I want to be able to disassemble this thing without taking all the pieces apart. That would just be a nightmare. So if I don't want to have to disassemble every planet every time I take it apart, then the planets can be only so big, because the mount bolts here that mount this structure onto this structure, they have to be accessible when the planets are in. Now I went about as big as I could, and I think there's going to be some jiggling involved, right? You have to put the bolt in and then jiggle the planets around a little to get the planets lined up so that the bolt will slide in. But I'm trying to get as much gain as possible. The outer tire rides on the axle on these bronze bushings, and of course there's one for the front too. And here is what you would call the outer portion of the Sun planetary. This would be equivalent to a ring gear. So this small piece, one of the reasons I picked chain planetaries is they can take an enormous amount of load, and they don't really weigh that much. And the reason is this, for instance, this disc here is made out of aluminum. It has 54 teeth that are always engaged. So unlike other gears that only have a few teeth engaged, this one is going to be virtually impossible to strip. So the planets are fixed, the sun spins, and as a result the outer is going to drive the wheel. And so let's show that. So there's the wheel interface. This system right here should be able to be built up and assembled as a complete set. And I would spare them that way. I would keep these set up as spares in that way. And the last two pieces I want to show here are actually going to be welded together. Well, obviously the tire's not welded, but there's a central cylinder made of aluminum, and the back is just a free-floating end piece like the front, except that it doesn't connect to anything. It's similarly designed. I use the same structural analysis to prove out the strength of them. The tire itself, in my iterations, what I did is I went around and I found a bunch of go-kart tires that were about the right size as I wanted, and I ordered one of each one. And it turns out one of them had the perfect inside diameter. So it fits this 8-inch diameter, outside diameter aluminum tube, and the inside diameter of the tire was about 7.9 or 7.95. So there'll be some grab on it when I try to put it on. I tried slip fitting one of the tire pieces over some tube that I had, and it looks like it's going to do well. And then I'll end up using some form of fastener through the tire to make doubly sure that it doesn't spin. And when this is all assembled like this, what you're going to have is I'm thinking you're going to have a pair of wires coming out one side, which is the power plus and minus, and then a set of wires coming out the other side, which are the serial communication wires to the speed controllers. Now those serial communication wires are going to have to go to wireless receivers, and I've looked at a couple of those Bluetooth systems that look very simple. and that has to float. Obviously, if this is going to be on an omnidirectional drive, then the wiring, the power wiring has to go through some sort of slip rings, or you could do wire wind, but if you did wire wind, it would limit the travel. And right now I want to try and see if I can do brushes to get the power across. So that's the basic design. I'm sure there'll be little mods as I go along, but we're going to try and mock one up and see how it works.